Hello, my name is John Broadwell, and I'm an independent consultant focused on medical device development and embedded systems at my company, Broadwell Consulting Inc. Today we're going to take a look at one of the Serial Wombat 18AB chip's pin modes, which is capable of directly measuring a resistance to ground, which is a bit unusual in this space. Right off the bat, you should understand that this may not be a replacement for a custom resistant measurement circuit such as a Wheatstone bridge. There's a lot of limitations. You can only measure resistance up to about 60 kiloohms, and the accuracy is not going to be spectacular due to variances in the Serial Wombat chip hardware. However, it is absolutely free. All you have to do is hook up resistance between the pin and ground, and it works pretty good for a lot of applications. This particular measurement is how the Serial Wombat chip determines the I2C address to use by measuring resistance on its address pin. There's one example for this in the example area, and that's example 1. Let's take a look at that now. First of all, we should know that there's a link in there that will take you directly to the GitHub IO page that talks about the Serial Wombat resistance input class, and it talks about all of the interfaces. For the most part, they look an awful lot like the Serial Wombat analog input. So in this example, we'll instantiate a Serial Wombat chip. In this case, we're on address 6B. We'll instantiate a resistance input. We'll call it resistor 0 since it's attached to pin 0. And for the purpose of this demo, we'll also instantiate a Serial Wombat TM1637 display. There's other examples and a video on that pin class as well that'll allow us to see the result over on the bench. We'll start up our I2C bus. We'll start up the Serial Wombat 18AB chip on I2C address 0x6B. We'll start up the display. Again, look at the other video and example for that. And all we have to do on the resistor is call resistor begin 0. We'll go into a loop, and once a second, we'll read the average ohms. It takes an average of 4 samples for each average, and it takes 20 samples per second normally, because this is a bit slower and it has to monopolize the A to D converter for a period of time because it has to hook up to a current source internally and some other things. Each time we take a measurement, we'll clear the display and print it to the display. And so that you can use this example without a display, we'll also dump it out the serial port. Not much to it. Let's take a look on the bench and see how it works. Here we can see our circuit. We have the Serial Wombat chip with all of the support components, the 3 capacitors, the pull-up resistors, the pull-up on reset. We're getting our power from an external 3.3 volt power supply coming into the breadboard. The whole thing's being driven by an ESP01 with its I2C lines tied up to the Serial Wombat chip. We've got a TM1637 display being driven by the Serial Wombat chip. And I've got 2 alligator clips here, one of which is tied to ground, one of which is tied to pin 0 to match up with the sketch that we showed earlier. You can see that the sketch is showing the resistance measured on the display, and that right now we're getting about 60 kiloohms, which is the top of the range for this particular measurement. So if we short these 2 guys together, that should be 0 ohms, but we see we've got an offset about 300 ohms, and we'll see that across all of our measurements. So let's hook up a resistor. Clip one side there, clip one side on the other side. And what is the size of that resistor? It is 1300 ohms, and we know we had a 300 ohm offset, so that's about 1000 ohms. And we look at that and we say, okay, black, brown, red, yep, that's a 1 kilo ohm resistor. Pull up another one. And this one's 5345, and I look at that, and it's green, red, red, so that's a 5.1 kilo ohm, and so again, minus the 300, we're quite close. Try out this one. Black, brown, orange, that's a 1 kilo ohm, and it's coming in right at 10,000. So that one's actually rating about 9,700, which is close to within range for the 1% value of this resistor. Finally, here we have a 10K pot. And you'll notice that I am not doing a voltage divider. I am only measuring 2 pins, the wiper and one side of the potentiometer. We will hook that guy up. And it looks like it's buried the needle on one side. As we turn this, it increases to 10K. So, and actually it's not quite going edge to edge with this particular pot. It's a cheap pot. That's not unexpected. So, but this is a great way to add a potentiometer if you didn't want to spend the extra constant current to have a voltage divider running through it all the time. So that worked pretty good. Let's give a little bit of background on why the input resistance measurement mode has the limitations that it does. To make a resistance measurement, we use the PIC 24FJ256GA702's charge time management unit, which essentially provides a 55 microamp source that we send out the analog pin during an analog measurement. It goes through that resistor to ground. Because of Ohm's law, V equals IR, we get a voltage generated on that pin, which is 0.000055 times whatever the resistance is. As we can see in the data sheet here, there is no minimum or maximum specified for this 55 microamps. So Microchip doesn't certify that it's going to be within any kind of range. All the samples I've tested have been pretty close, but it's not perfect and it's not even specified. So we multiply that and we get an absolute voltage. Now, the way that the analog to digital converter works is it measures between your high source voltage, which might be 3.3, might be 3.0, might be 3.1, you don't know, and ground. In order to make an absolute voltage measurement, we have to take that analog to digital converter ratio and then also look at a ratio of a known fixed voltage against the voltage source for the Serial Wombat 18AB chip. That internal voltage is the PIC's internal band gap reference, which nominally is 1.2 volts, but could be as low as 1.14 or 1.26. So right off the bat, that adds a potential of up to 5% error to the measurement. So you compound the 1% error that you get from a 1% resistor, plus up to 5%, plus some unknown amount of error in the 0.00055 amp current source, and you get a good amount of error. Again, not a perfect way to measure a resistance, but pretty awesome if you want to tell the difference between a high resistance, low resistance, as we do with the address pins, or do some other operation where you want to tell qualitative resistance ranges as opposed to perhaps a precise value. It appears that we can do a calibration on the chip at room temperature to better calibrate the internal band gap reference and to get an idea of exactly how much current that particular chip drives in the CTMU mode. And it's likely in the future that I will sell hand-calibrated chips that I run through against precision voltage references and resistors, and then store those values internally to potentially give you a better result. How much better? I won't say, but I think it probably will be better, and that will be a slightly premium chip that will be for sale. If you have any questions about the Serial Wombat resistance measurement mode, leave them in the comments below. If you like the video, like it. If you're using this mode for a project, by all means, please tell me what it is. Send me some pictures to the email help@serialwombat.com. I'd love to feature your project in a future video. So everybody have fun and keep making stuff. The Serial Wombat firmware is available on GitHub and is constantly being updated. Subscribe below so that you can see the latest features and videos that come out as we fix bugs and add new features. The Serial Wombat open source project was created by Broadwell Consulting Inc. Broadwell Consulting Inc. provides help developing medical devices with a focus on developing embedded firmware, which is compliant with IEC 62304, ISO 14971, and ISO 13485, as well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting. Support requests for Serial Wombat should be sent to help@serialwombat.com and will be answered on an as-available basis. Also, feel free to leave your question in the comments below.